All right, let's rock and roll. Welcome to another episode of Space Nuts. I am your host, Heidi Campo, today, filling in for Andrew Dunkley, and I'm here with Professor Watson, astronomer at large. Professor Fred Watson.
Actually,
Let's
Fred,
just say Watson. If I just say Watson, it makes it sound like this is a mystery podcast and not a space podcast.
Yeah, that's right. Elementary, my dear Watson.
All right. Well, speaking of mysteries, we have a lot of really good questions with mysteries for you to solve today. And our first question comes from Rusty from Donnybrook.
Hey, Andrew and Fred, it's Rusty in Donnybrook. I'm sitting out in a beautiful clear night and looking due north. I can see Mars there. And it's quite close to the twins, Castor and Pollux, the Gemini twins. It's closest to Pollux, which is, and it's an orange giant star, and it looks redder. Pollux looks redder than Mars. And if we look to the southwest from there, we can see Betelgeuse, part of Orion. That one looks redder again. So my question is, when you take a picture through a very large telescope and you can really see these colours close up, how colourful are they? Is a red giant as red as a tomato or a pillar box? And what about the blue stars? How blue do they get? Is it like when we call them red and blue, is that fair dinkum? Anyway, have a good one.
And so I can imagine, so Rusty is one of our regular questioners, Donnybrook in Western Australia, and always asks intriguing questions. And I think what he's thinking of here is if you sat yourself at the eyepiece, for example, of the biggest telescope in Australia, the one that I used to be astronomer in charge of up in Coonabarabran, with its 3.9 meter diameter mirror, and you looked through an eyepiece at some of these objects, what would you see? Would you see the colors more richly than we do with a small instrument? And the answer is a little bit, I suppose, disappointing, really, because the colors are still subtle. Looking through a very big telescope, and I've actually done it with the Anglo-Australian telescope, it's quite hard to get an eyepiece on a telescope like that because it's festooned with spectrographs and autoguiders and instruments of all different kinds that don't have an eyepiece on them. But when you look through, yes, you do see the colors, Mars looking red, Sirius looking dazzlingly white, some blue stars, the jewel box, which is a cluster of stars in the constellation of the Southern Cross, so named because it's got stars of different colors, including a particularly red one, which is a sort of ruby-colored stars. Those colors are exaggerated, but perhaps not as much as you think they would be, Rusty. They don't go deep red or anything like that. The colors are still as subtle as you see them, but if I can put it this way, it's just like sliding up the saturation button on your color editor in whatever photo editing system you use. Slide up saturation a bit and you get a bit more color. Likewise with the size of a telescope. What you might be surprised at, though, is that the detail that you see with a big telescope is not as fine as you'd expect. And that's all about the way the atmosphere behaves. The atmosphere, in terms of the way turbulence in the atmosphere spoils the view through a telescope, it's actually far less forgiving of a big telescope than it is in a smaller one. A smaller one, you might just see the object moving around, but you can see it quite sharply. Whereas with a big telescope, it just tends to blur it out. It still moves out.
Would have
blurred.
Totally thought it was the other way around. I would have thought those big telescopes were like high def, 4K, perfect picture.
They are with modern technology. These new, not really new, they've been around for 30 years, but it's only within the last decade that they've been perfected, what we call adaptive optics systems, which actually, it's all about the turbulence. The telescopes themselves, if they were in space, they would reveal perfect images, exactly like the Webb telescope or the Hubble telescope do. But because they're at the bottom of an atmosphere with a lot of turbulence in the air, even on top of mountains, there's turbulence. That's what spoils the view. But modern technology lets you sense that turbulence. It lets you see what is the distortion that the atmosphere is providing. And then just like a pair of noise-cancelling headphones, it cancels it out. It provides the opposite signal, so it cancels out the turbulence. It's very hard technology because you have to measure the star, use what's called a reference star, which is sometimes artificial. You've got to measure that star 1,000 times a second for this process to work. So it needs very fast readout sensors, much faster than what you find in, for example, a mobile phone. But the same sort of thing, but they're reading out 1,000 times a second at least. In fact, sometimes twice that.
That is so incredible. Every day I'm so proud of humanity for what we've come up with. It's just fantastic to think. And if we all just work together as a team, this would be, we'd already have, gone past our own solar system by now if we all worked as a big team. That is so incredible just to think of all the details of these technologies.
Let's take a little break from the show to tell you about our sponsor, Saily. As you know, my wife and I like to travel. We've been overseas quite a few times in recent years. Now that I'm retired, we plan to do more. And one of the things I really like to do is make sure I've got access to mobile phone data, particularly when I'm using maps, because it's so easy to get lost when you're in a very unfamiliar environment. Some time ago, we did use an eSIM service from another company, and it did not work, and it left us in a very difficult position. We were high and dry, and we were not happy, and we didn't have any backup service, which was also very, very disconcerting. So we had no one to call to say, look, this doesn't work, what can you do? And it just left us in a really difficult position and left a nasty taste in our mouths as well. I wish I'd known about Saily at that point in time. Saily offers an eSIM service covering 180 countries. With an eSIM, you don't have to physically change the SIM in your phone. You just download it and it works when you switch the service on in whatever country or regional area that you want to serve the internet on. And it's as simple as going to your App Store or Play Store, downloading the Saily app and choosing whatever service you need from whatever country, and away you go. Simple as that. Right now, there's a discount available to Space Nuts listeners. And all you have to do when you buy whatever coverage area you've chosen is put Space Nuts, the code word, in at the checkout, okay? So Space Nuts at the checkout will get you a discount as a Space Nuts listener on Saily. I highly recommend when you're overseas to use a service like this. So if you would like to get that discount as a Space Nuts listener on Saily, download the app from your Android or Apple device, and when you get to the checkout, make sure you put Space Nuts in as the code word for the discount. No matter where you are or what you plan to do, this is a service that will back you 100%. And you can read all about it as well at saily.com/spacenuts. That's saily.com/spacenuts, and get all that stress out of your overseas travel. This is one thing you won't have to worry about. All the details, of course, are in our show notes. Now, back to the show.
Okay, we checked all 4 systems and skiing was a go.
Space Nuts.
Well, our next question is from Dan from California. Dan the man. He says, I was reading about gamma ray bursts and how devastating they can be should they hit Earth. Can you explain why gamma ray bursts become less lethal the further away they are, because the majority of space is a void rather than dust, I assume? The same goes for radio waves, where over distance they get weaker and weaker. Is this really due to dust and gas that are weakening the signals? Thanks.
Yes, it's actually nothing to do with dust and gas. Dan, sorry, wrong name. Reading the wrong bit of the question. Dan, the reason why things get weaker the further away you get is because of a fundamental law of physics, which is called the inverse square law. And that is that if you double the distance that you are from a source of gamma rays or radio waves or whatever, you double the distance, the signal drops by a factor of 4. It's the square of the distance. That's why it's called the inverse square law. So double the distance, you get, a quarter of the signal. And if you then double the distance again, it goes down by an equally large, it goes down by the square of the new distance. The new distance is 4, so it goes down by 16, a factor of 16. And that's why all these signals get weaker. Dust and gas do impact on them. And for example, perhaps the best example of that is the center of our Milky Way galaxy at a distance of about 25,000 light years. We can't see the center of that with visible light telescopes because of the dust that blocks our view. It's dusty in the Milky Way, and the center of our galaxy is hidden. Infrared radiation penetrates the dust, and that's why we can actually see the center of our galaxy in infrared, but not with visible light. So dust certainly has an effect, but it's the distance that is the real effect. This inverse square law means it's the square of the distance by which it drops every time you move away.
I wonder if that's everyone has that crazy friend that always is just on speakerphone. They're like, oh, I don't want to hold the phone up to my head. I don't want the waves to get me. I'm going to hold my phone, 2 feet away from my face, and I'm going to shout into it so everybody can hear my conversation. Who knows? Maybe they may be onto something.
Well, you're right that sound waves also are affected by the inverse square law. So if you double the distance from the person who's yelling into their phone, then it's going to go down by a factor of 4. So that you try doubling the distance twice, and it'll drop by a factor of 16.
Yeah, I can't hear you. All right, our next question is from Mike from the UK.
It's Mike Cupid from the UK here. A very quick question, if I may. I have heard many, many questions over the years into you guys about terraforming Mars, which is obviously something that is beyond our capability, but a lot of people dream about. What about terraforming Venus? It's not something I've heard a lot about. Now, obviously, it's probably still beyond our capability, so let's just talk sort of theoretical, but would it just be a case of blocking out some of the sun's rays to cool the planet down and potentially reverse that runaway greenhouse effect that's happening on Venus? So potentially, just thinking outside the box, possibly collide two asteroids together and let the debris catch in the orbit of Venus, blocking out some of the sun and then cooling it down, or potentially even sort of build a structure to block some of the sun's rays. And the other question as well, and like I say, I know this is probably beyond our capability, but if we did manage to do that and cool the planet down, if we could get the conditions on Venus to be similar to what they are on Earth, which would probably never happen anyway, but would it stabilize, or would the greenhouse runaway effect happen again? Is it too close to the sun to hold a stable atmosphere and a similar temperature to Earth? Love the show. It's my favorite podcast in the world. I listen to it all the time. I think I've listened to just about every episode. So regardless of whether you answer my question or not, please keep up the good work. And thank you very much for your time.
Yeah, that's a great question, Mike. Terraforming Venus. Venus is so different from the Earth in its natural environment that it's hard to think of you can think of more different planets because exoplanets are even wider in range. But yes, here we've got a planet with a surface temperature of about 460 degrees Celsius, hot enough to melt lead, hot enough that the rocks probably glow a dull red as well because of that temperature. and an atmosphere whose pressure is 100 times the pressure of the Earth's atmosphere, laden with carbon dioxide. And just to add to that lovely benign picture, in the upper atmosphere, it drizzles sulfuric acid. So you've really got a hellish circumstance for anybody on Venus. How could you terraform it? Well, you're right that the fact that Venus is, it's much nearer the sun than we are on Earth, that contributes and goes back to the question we were just talking about. It's the inverse square law. So you're actually getting far more radiation than you might think just by being, a few tens of millions of kilometers nearer to the sun. The idea of blocking the sun's light is something that has been suggested quite seriously on Earth in order to reduce the carbon footprint that we're all making. If you launch, I'm trying to remember who suggested it at first. It's somebody I know, and I can't remember who it was. But if you launch a swarm of spacecraft and put them at what we call the L2 point, the second Lagrange point, which is a stable position between any planet and the sun, where the gravity balances out. You put this swarm of spacecraft. This was suggested for the Earth, but it would equally apply to Venus. You could do the same thing to try and block down the sun's light. I'm not convinced that that would actually have any positive effect on the atmosphere of Venus. It would certainly cool the radiation that it feels from the sun. The carbon dioxide rich atmosphere would still act as a runaway greenhouse atmosphere. So I think you would still have these very high temperatures, and I don't think there is any technology we could imagine that would change that. And if you were going to think about terraforming somewhere, and I should say it's pretty well impossible, but if you were going to think of it, Mars will be a better bet. You'd have to keep on terraforming it, though, because Mars doesn't have enough gravity to hang on to an atmosphere like the Earth's. So I think you're right that you would not lose the runaway greenhouse effect. It would not go away, basically.
Yeah, Venus is really, I'm sorry, Venus, it's a terrible, terrible planet. It's really, I think, pretty nasty as far as everything that's going on that planet. But, we did historically used to think that was going to be the most similar, closest planet to us. And then we flew some satellites by it and we're like, oh, that's terrifying.
Okay. But yeah, you're right. I mean, it is similar. It's virtually the same size as Earth. There's some new research just been released, actually, which I nearly thought we might talk about on Space Nuts. And it's about the crust of Venus. Because like the Earth, Venus has, we don't know what's at its core. It doesn't have a magnetic field, so it's probably not an iron core like ours. A mantle, a sort of soft rock above that, and a crust. And we live on the Earth's crust, for example, which is not very thick. It's 30 or 40 kilometers thick, which is quite slender. But the thinking is that Venus has a much thicker crust, and that there is what we call convection, this heat rising or material rising because of heat, convection taking place in the crust of Venus, which may be why Venus has the largest number of volcanoes of any object known in the solar system. Now, we don't know if they're active or not. This is just counting craters from radar measurements of its surface. It's got the largest number of certainly volcanic structures. And the thinking now is that comes from convection in the crust rather than convection in the mantle, which is what we have here on Earth. Just a little factoid about Venus that I think contributes to its reputation as Earth's ugly sister.
Well, that is such a fun fact, though. I never knew that about Venus.
3, 2, 1.
Space Nuts.
Our very last question is from Todd. He's from Utah. I am also from Utah. So Todd, thank you for representing our little state. Hopefully you're winding up for some good weather there. I know springtime in Salt Lake's always really beautiful. And I don't know if you're a skier, if you got some good skiing in this season, but That's my little plug to a fellow at Utah. His question is, hello, gentlemen. I have a question about the double slit experiment. Well, truthfully, I have many questions about it, but let's just focus on one for now. I have seen that some have done this experiment by shooting individual photons at the double slit one at a time, yet this still produces an inference pattern. This, of course, boggles my mind. I've read that this is an example of quantum superposition, and that somehow those photons are interacting with themselves. Can you and Fred please elaborate on what exactly we understand is happening here? Is this something silly along the lines of photons not being bound by time? Speaking of time, thank you for yours. Finally, I have an observational joke for you. In 3,025 years from now, life on Earth will either be really good or really bad. It's 50-50. That is from Todd from Utah, USA. Thank you so much for the joke, Todd, and the question.
I like the joke a lot, but nobody I've told it to so far gets it. So I'm obviously losing something in the retelling there. It's a good one. Thank you,
I think
Todd.
you need a better audience. They're not laughing at that. They're
Maybe so. Yeah. Anyway, the question, this is, and just to, sort of fill in the backstory, what are we talking about with the double slit experiment? If you pass beams of light through two slits, under the right circumstance, they will interfere with one another. And that means we will see bright and dark patterns because of the way the waves mix. So waves of light basically can add together or can cancel out. And it's where they add together and cancel out that we see these bright and dark patterns. I was very keen on interferometry, the technique of doing that and making measurements by it when I was a young student. So that is basically, it was the proof of the fact that light is a wave motion, because Newton thought it was particles. But it was demonstrated not long after Newton's time that it was a wave motion by virtue of this double slit experiment at the beginning of the 19th century. But now we know that light is particles and waves. And sometimes maybe the way to imagine it is as wave packets. These photons, particles of light, are sort of also a wave. That was the way we kind of looked at things perhaps in the 50s and 60s, that photons were packets of waves, because that would let you then use particles, but that they would still do this interference trick. So that proved they had a wave motion. Along comes quantum theory that says particles are basically made of waves. They're not just packets of waves, they're made of waves in a very odd way. And that experiment that Todd has referred to is the one that tells you that there's something really peculiar going on. Because if you shoot single photons through this double slit experiment one at a time, so that they never come together in a wave method, you still get the interference pattern building up that proves that they're waves. And I think, Todd's comment about, is it something silly like photons not being bound by time? In a way it is. I think it's more about the mystery of quantum entanglement, that these particles are entangled together, which means that they behave like a single particle. So if you've got one going through one side of the slit, or one half of the slit, one going through another, they're still part of the same object, even if they're going through at different times. So that's perhaps, yes, that they're not bound by time in that sense, but I think it's more to do with the phenomenon of quantum entanglement, that things behave as though they're a single quantum object, even though they're quite separate. They're separated sometimes by very large distances, but they have common behavior between them. And I think that's how the double slit experiment arises when you use photons, separate photons. I've probably left you completely cold then, Heidi.
I thought this was fantastic, and it all went completely over my head.
Yeah,
But
it's one of the sort of fundamental experiments of physics that tells you that light is both a wave and a particle, but the two somehow mix together in a very mysterious way. I think that's the bottom line.
Okay, well, I think I can understand that it's a mystery and they miss. I understood those words.
Yeah, that's...
Oh, wow. I mean, once again, thank you so much, Fred, for you always take such patience and care with answering these questions and making things make sense and just making it fun and relatable and just exploring and thinking together. So thank you so much for everything that you provided us with today.
It's a pleasure, Heidi. Thank you for being the kernel of the show by keeping it going. I mean, KERNEL rather than CON.
English language is quite interesting. Well, thank you so much, everybody, for listening in to today's episode, today's question and answer episode of Space Nuts. And we will catch you next week. I will be back here again for just a couple more weeks, and then you'll get your dear, sweet Andrew back. But until then, you're stuck with me. Thanks again to those of you. I heard that a few of you wrote in with some kind words about me. So thank you so much. If you guys had compliments, I appreciate that. But until next time, we will be signing off. Thank you so much.
Thank you, Heidi. And thanks also to Hugh in the background there, back in the studio, keeping us all honest. We'll see you next time, Heidi. Bye for now.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.